Okay, so I think we can start. So welcome to everybody. So this is going to be the basic string theory course. So I would like really to start from scratch, but still to give you some concrete taste of worksheet techniques in string theory. And so this series of lectures are meant to be important for two main reasons. So the first reason is that many of you, as many of you already know, the things you will study during your PhD, many of these things will have their origin or rationale in string theory. So it is definitely important to see what these things are. And the second reason is that some of the fundamental aspects of string theory are still subject of active research. And by this, I mean research on superstring amplitudes, correct treatment of infrared divergences in string theory, strings in Riemann backgrounds, possible exact analytic control on non-perturbative physics, the questions for background independence, and other things which may also be related to the so-called string field theory. So the aim of the lectures that I'd like to give is to be useful on both sides, okay, or on both of these points that I have mentioned. And so I hope this course, this series of lectures, will be okay for different kinds of students, which may have different backgrounds also. But at least I think that I'm just assuming basic knowledge of general relativity and basic knowledge of quantum field theory, whatever that means. And so that's as I already put in the website of LACES. The material I'm covering is all contained in the standard books of string theory, the Pulczynski one, and the Blumenhagen Lust-Theisen. This is very complete and is the most modern book. The Green-Schwarz-Witten is always a very good reference. And for those of you who would like to have a quick introduction just for the bosonic string, I acknowledge the lecture notes by David Tong, which are very, very well written. And so let's go to the plan of the lectures. So this is more or less the material that I would like to cover during these 15 hours. So we will start with the Polyakov path integral, and we will see how we can make sense of the BRST quantization of string theory, on at least the bosonic string. Then I will spend some time explaining the basic facts of two-dimensional conformal field theory. Then with this material, we can have a concrete look at the realm of bosonic strings and bosonic d-branes, and we will see what is what happens in this bosonic world. Next, I will upgrade to the superstring, and so in this course there is no time to do all the 5 superstrings. So I decided just to concentrate on the type 2 superstrings, so that we can discuss worksheet supersymmetry and target space supersymmetry, and how this emerges from string theory, from worksheet supersymmetry. Then we will be able to discuss relevant aspects of the branes and their Riemann charges, and we will see why they are so important. And the last part of the lectures will be devoted to some concrete computations in string theory. So first we will try to attack the simplest 3-level amplitudes. Okay, so we will see how the strings interact also, and I would like to also review and treat one loop vacuum amplitudes and to see the modular invariance of string theory. So if you don't have questions, we can start. And so that's lecture 1, the Polyakov path integral. And okay, so what's the idea? We start with the idea of strings. So strings are associated to some function, some of two variables, tau and sigma, which describe the embedding of a closed two-dimensional surface, which have the topology of a cylinder in the case of closed strings, or a strip in the case of open strings. So these maps, so these are two-dimensional surfaces that are spanned by this coordinate sigma and tau, sigma and tau. And these maps describe the embedding of these two-dimensional surfaces in Minkowski. So that's R1, D. And so these maps here is describe the embedding of some of this surface in space-time. I'm sorry for my very bad handwriting. Okay, and the same is true for, of course, the open string, which will describe a surface with two boundaries. So notice immediately that these surfaces are called world sheet. Okay, so this is the world sheet. Notice that for the open strings, the world sheet has two boundaries. So these are boundaries. Okay, so these maps are not completely free, but are chosen to follow from an action. So on these two-dimensional surfaces, there is a natural action for these maps, x mu, and this action is to start with the Nambu-Goto action, which is given by this expression, 1/2 pi alpha prime, the integral in d2 sigma. So now I'm collectively calling tau and sigma. I'm just calling them sigma collectively. And the important part of the action is minus that of G. What is G? G is the induced metric on the worldsheet, which is just the alpha x mu, the beta x nu, eta mu nu. Okay, so you see that this action is the generalization of the point particle action for the geodesic equations. So it's immediate to see that the classical solution of this action will be minimal area surfaces. Okay, now as many of you probably already know, you know that this action is difficult to quantize. Why it is difficult to quantize? Well, because it's not in the standard form for an action that we know how to quantize. Especially here, it's not clear how here we extract a free part, a quadratic part, and then interactions. And so what we will do now, we will write another action that is classically equivalent to this action that we just wrote, to this action here. And this other action that we are going to write is this form as P, where P stands for Polyakov, as we will now argue. And so I'm going to have the same measure, but now I couple these maps X mu, I couple them to a two-dimensional worksheet metric, which is completely independent from the pullback of the metric from this metric here that I defined here. So it's a new degrees of freedom. And so essentially I'm coupling in a generally covariant way in this form, the beta x nu, eta mu nu, okay? So now this action is of course, is different from the one that I already wrote, and it has two fields. One field is the embedding coordinate x mu that we already had before, and the other one is this metric h alpha beta. So now I will have equation of motions. So I can first vary the action with respect to the metric, and since this is generally covariant action, this will give me the energy momentum tensor of the theory. So this is sorry, let's say like this. So if I vary this, I get as an equation of motion T alpha beta, which if you explicitly vary with respect to the metric, you will find that this is G alpha beta minus 1/2 H alpha beta times H dot G. So by this, I mean the full contraction between these rank 2 tensors. And okay, where G alpha beta it is being defined here. And the other interesting equation of motion is the one that I get by varying with respect to x. Okay, so if I vary with respect to x, I have to pay a little bit attention. So I have really an equation of motion for the bulk degrees of freedom that is obtainable in the usual way and reads. This is how it looks like. Okay, so this is for the bulk. But since I am allowing my worksheet to have a boundary, so I have to pay attention also to the variation of I mean, to build up a consistent variational principle, also taking into account boundary degrees of freedom. And if I do this, essentially I find a boundary component for the equation of motion, which looks like this: H sigma beta, the beta x mu, the variation of my field x mu evaluated at the boundary of the worksheet. This should be 0. Okay, so if I want my Polyakov action to be extremized, I need to impose these 3 conditions. Very good. So now I have. So in my lectures, I will propose you many exercises along the way, and I suggest you to do them just to gain some control on the things that we are seeing. So here is the first exercise for you. And then we can discuss these exercises if you want in many occasions. So now I would like you to use this equation of motion here for the metric. Okay, so I would like you to use T alpha beta equal to 0 to show that S Polyakov, this action that we just wrote here, is in fact equal upon the use of the equation of motion for the metric to the S Nambu-Goto that we defined here. Okay. Okay, so maybe I can just give you some of the things that you will need to know. To do this, you will have to remember that the variation of the determinant of the metric can be written, for example, as minus h times h alpha beta delta h alpha beta. And then you will have to carefully use this equation here. Okay. Okay. So now it's time to discuss the symmetries of this action. So perhaps I can copy, since I have some space, I can copy this action for your convenience. Here, and we can discuss the symmetries. So we start with so this action has been coupled to a two-dimensional metric in a general covariant way. So it has, of course, diff invariance. So what is diff invariance is, so these are general coordinate transformation. Let me denote them by delta D, where D stands for diff. So first of all, the variation acts on coordinates themselves in the and transforms coordinate in general functions of the coordinates. Infinitesimal functions, here I'm considering infinitesimal diffeomorphism, of course. Then this diffeomorphism also acts on the embedding maps, which are, from the two-dimensional point of view, they are just scalars. And so they transform as scalars in this way. And finally, the metric is a metric, so it transforms as any metric in general relativity in this way with the covariant derivatives plus delta beta psi alpha. Very good. So now this that's not the whole story for the local symmetries of this action. This action has also another local symmetry, which is the Weil symmetry. The Weil symmetry only acts on the metric, in fact. In fact, the d Weil on sigma is equal to 0, and d Weil on x mu is also equal to 0. But the Weil acts on the metric by rescaling it, and in its infinitesimal form, it looks like this. Okay. So the finite form would be h, which goes to e to the wh. So it is a rescaling, a local rescaling of the metric. So the reason why this action is invariant under Weil transformation is really because we are in 2 dimensions, and that's another. If you can take it as a small exercise for you if you want. But the very reason is that in 2 dimensions, this combination here, the determinant, the square root of the determinant of the metric times h alpha beta is Weil invariant. And notice that this is valid strictly in d equal 2. If d is not exactly 2, even by tiny amount, then this thing is not true anymore, and there will be possible violation of Weil symmetries. Okay, so that's the whole story for the gauge symmetries. And now this action has also global symmetries, of course. From a two-dimensional point of view. And since here, so the global symmetries are essentially inherited by the properties of the embedding space where I have embedded my worksheet here. Okay, so this is R1D, so there is Poincare invariance. The Poincare invariance arises as a global symmetry on the worksheet. So there is Poincare, which is, as all of you know, can be written in this way, m mu nu x nu, and Poincare, of course, does not act on the worksheet metric. Okay, so if there are no questions, we can now proceed. And so now the idea would be to try to give a meaning at the quantum level to this action. Okay, so we'd like to make sense of this action quantum mechanically. Now, even before talking about what could be the interpretation of the path integral of this action, first of all, just to be able to define a path integral, since we have a gauge symmetry, the path integral cannot be defined properly unless we do some consistent gauge fixing of this action. Okay. And so why we need gauge fixing? But we need gauge fixing because we would like to understand what is the quantum meaning of this action. And in particular, we would like to be able to define, as in any gauge theory, something that I want to define in any gauge theory, even in space-time gauge theory. But what I would like to be able to define are correlation functions of gauge invariant operators. Okay, we will see later that this correlation function of gauge invariant operators will be associated to scattering amplitudes in space-time. But for the time being, I'm here. We are just interested in the fact that we have some gauge theory, which has this gauge symmetry. Okay, and we would like to be able to define the path integral with some gauge invariant operator inserted. So in particular, we will be interested in trying to give a meaning to objects like this, V1, Vn, where these V's are yet to be determined and discussed, the gauge invariant operators. And but if I want to give a meaning to this thing in the path integral sense, then I have to compute something like this. So functional integration on the matrix, functional integration on X. These are my quantum fields. And of course, these functional integrations, these measures is overcounting a lot because I have these infinite dimensional gauge symmetries. So I have to divide by the volume of the gauge group, whatever that means. Once I do this, then I can insert in the path integral my gauge invariant operators, and I can weight everything with my action, with my gauge invariant action. Okay, so just trying to be a little bit more concrete than this. How can I define what is this volume of the gauge group? Okay, a little bit heuristically, I'm going to define it just as this thing here, as the functional integration of the parameters of my gauge transformations. Okay, so my gauge transformations are here. Okay, one gauge parameter is psi, which controls the diffeomorphism, and the other gauge parameter is W, which controls the vial. Okay, So this is for diffeomorphism, and this is for Weil. Okay. So now, what is the strategy for doing this gauge fixing? It goes as follows. So if we look here at the variation of the metric, this and this, together with the fact that in d equal to h alpha beta has no propagating degrees of freedom, and this is because d minus 2 is equal to 0. So the trick is essentially to trade the integral over the metrics to the integral over the gauge group. Okay, because essentially all of the possible variation of the metric can be obtained by a gauge transformation. That this is the meaning of having no propagating degrees of freedom. Okay, to be a little bit more concrete on this, we can take a generic variation of my metric, and we are going to see that this variation, in fact, can be written as a gauge variation, which we are going to define shortly. And then, okay, so this is essentially, this should capture most of the variation of the metric. Actually, what it happens is that there is a small finite dimensional part that is left uncovered by this gauge variation, and this is what the so-called modular variation, which we are going to define shortly. Okay, but for the time being, just accept this decomposition of the most generic variation of the metric. So this is a gauge variation, and this is a modular variation. Okay, so this gauge variation, I can read it here from this transformation. And in fact, it turns out that it's convenient to write it in the following way: delta gauge h alpha beta equal to the covariant, this covariant symmetrized variation here, and then there is the Weil part. And as I was telling you, it is customary to assemble these two variations in two structures. One is going to be called P1 psi alpha beta minus big omega h alpha beta. So these are just names, and now I'll give you the definition of these objects. So this P1 psi alpha beta is just 1/2 times this guy here, this guy here, but I take out the trace because then it becomes a nicer object if I do this. So I take out the trace, and therefore then this trace has to be compensated in this other object, the big omega, which is the small omega minus 1/2, the covariant divergence of the vector field psi. Okay. Okay, so as I was telling you, these are just definition. Note that P1 as an operator P1 is a differential operator that acts on vector fields. And associates to them symmetric, traceless, rank 2 tensor. Okay, so okay, that's just it. So this defines completely what is the gauge variation of the two-dimensional metric. Very good. So what is now, what is on the other hand, what the delta M, the moduli variation? I'm going to define it as a variation which is orthogonal to delta gauge. Okay? And what do I mean by orthogonality? I mean that for every chosen fiducial metric H alpha beta, for any chosen metric, the space of fluctuations around these metrics, the space of variation of this metric is a vector field, and this vector field is a natural scalar product. Okay, so the scalar product has this form: delta H1 comma delta H2. Okay, so I have delta H1 and H2 are just variation of this metric, so it means that a generic metric will be written as some fiducial metric plus delta H alpha beta. Okay, so these are two possible variations of this metric, and so these two possible variations form a vector space, and this vector space is a metric on it. Is the metric on the space of metrics, which is defined in this way: d2 sigma square root of h hat delta h1 alpha beta delta h2 alpha beta. And so then by this equation, by this definition, the del M H is defined to be orthogonal to the gauge variation. Okay, so this has to be true. Okay, so if we look explicitly what this thing means, it means that, so here I have P1 psi minus 2P1 psi, sorry, 2P1 psi minus omega H, comma, delta M H. Okay, so this gives me two conditions because the gauge variation of the metric is done with two ingredients. Okay, so the first simple thing is the one that comes from the while part. Let's say is this part here, and this gives me this equation: H hat alpha beta delta M H alpha beta equal to 0. So I learn that moduli variation are traceless. Are traceless with respect to the chosen fiducial metric.
Sorry, Carlo, could I ask a question, please?
Please.
So this is Hodge decomposition for these two different things. I'm just wondering, in this, you're also compensating for the fact that there are no singular elements in the maximal torus.
Yes, okay, these global things are somehow so there is something that I'm not really considering at the moment. So there is part of this gauge group that I'm not considering, which are these conformal Killing vectors, but we will discuss about them later. Okay. But still, I'm yes. Okay. Okay. So then we look at the other variation, at the other piece, which is this one. This one gives a more interesting. Gives a more interesting equation, because you see that from here I can essentially take this P1 and apply it on the other side of the scalar product, and where it becomes P1 transpose or adjoint, however you want to call it. So this one really defines me what is the real equation for the moduli. The H alpha equal to 0. So if you just go and see what this P1 transpose operator is, okay, you should not be scared by this, because it is just given by this covariant derivative here, del m h beta alpha equal to 0. Okay, and so it turns out that the solution to this equation, this is a finite dimensional space. Contrary to the infinite dimensionality of the gauge variation, for example. Okay, so let's say that modulo of a finite dimensional space, all the degrees of freedom of the metric are pure gauge, but one has also this small part. So here is a picture of what you have to have in mind. So essentially, in the space of, so this is a picture for the space of metrics, and there is this finite dimensional surface here, okay, which is essentially given by the choice of a fiducial metric, which will depend on these moduli coordinates, okay. And then you have to imagine the space of metrics as a fiber bundle, whose base is given by the moduli space, essentially, and the fiber is given by all the possible gauge variation. Okay, so a picture for the two variation of the metric is as follows. Okay, so the moduli variation is a variation which is tangential to the base manifold, which is the moduli space, and the gauge variation is a variation along the fiber, and so there is this notion of orthogonality here that is exactly given by this metric that I have defined here. Okay, so now that we have this decomposition, we can take our dh alpha beta and write it as dh gauge dh moduli. And now I know exactly how these things are expressed in terms of the gauge parameters, for example. Okay, so this dh gauge is essentially this is just the measure of the metric along the gauge orbit. Okay, so this is just by change of variable can be written formally as in this way: the gauge h over I'm writing formally in this way, okay, where these are the diffeomorphisms and these are the vials, and this stands for determinant times psi alpha dw. And in the same way, I can also write the moduli variation as this time a real determinant, finite dimensional one, because this guy just depends as a real function. So these are ordinary derivatives, in fact, times dti. Okay. So this is, of course, an infinite dimensional integral, but this is just a finite dimensional integral. Okay. Okay. So just to fix a little bit then the notation. So we have moduli. So what are these moduli that we have just defined? So they are the solution to this equation. Sorry. To this linear equation, which means delta beta delta mh alpha beta equal to 0. And so then you may be, since we are studying the kernel of P1 transpose, then you may be curious, and perhaps you would like to know about the so-called conformal killing vectors. What are these guys? These guys are just the solution to another linear equation, which is related to this linear equation here, which is the transpose of it, which is just P1 on psi alpha equal to 0. Okay, written in component, this means delta alpha psi beta plus delta beta psi alpha minus h alpha beta, the divergence equal to 0. Okay, very good. So it turns out that these two vector spaces, these two kernels, the kernel of P1 transpose and the kernel of P1, are related. The dimension of these two guys are related by a theorem that I'm just going to mention, which is the Riemann-Roch theorem, which says the following: the dimension of the kernel of P1 transpose, that is the dimension of the moduli space, minus the dimension of the kernel of P1, which is the dimension, the number of linearly independent conformal killing vectors, is a topological invariant on any two-dimensional surface and only depends on the topology of the surface. And the dependence is through the so-called chi, which is called the Euler characteristic. Okay, so in turn, this Euler number can be obtained in two dimensions in d equal 2. This again something that only happens in d equal 2. This Euler characteristic is in fact given by a very familiar expression, which is this one. So this is my two-dimensional surface, d squared sigma square root of h R2. So that's the Einstein-Hilbert action in two dimensions. Okay, as I was telling you, gravity is not propagating in two dimensions. There are no local degrees of freedom. So it turns out that this thing here is purely a topological term in two dimensions. But remember that our worksheet can have boundaries, so we have also to remember these, and then we have to correct the definition of the Euler characteristic with something which is good also when we have boundary, which is this thing here, where we have this k. Okay, so so just to say, this is the Ricci scalar in d equal 2, something that we are all very familiar with. And perhaps you may be a little bit less familiar with this other object here, which is called the geodesic curvature of the boundary. Okay, this guy has just like R, this guy has also a definition. So we can write it down because it doesn't take too much space. The definition is pretty simple. So if we have our piece of worksheet, okay, it has some boundary. So this is the boundary of our worksheet. On any point in the boundary, since in my worksheet I have a metric h here, on any point in the boundary I can define a tangent vector and a normal vector, t and n. Okay, and so this geodesic curvature is given by this expression here, T alpha, T beta, delta alpha and beta. Okay, and so if you never encountered this guy before, you may be curious to know how this definition gives you something that you know already. So I may propose you this very simple exercise. Okay, so take a disk of radius r with h alpha beta equal at delta fm, the flat metric, and compute the geodesic curvature. And if you compute the geodesic curvature, I guess you will find that k is equal to 1 over r, which will give rise to the notion of curvature of a. So is essentially the curvature is the inverse of the radius of the circle, which is locally tangential to your curve. In this case, the curve is a radius circle. Okay. Okay. Why I am spending some time on this Euler characteristic? Okay, first of all, by the Riemann-Roch theorem, but there is a reason why this Euler characteristic is very important in string theory. And the reason is that chi controls the perturbation expansion of string scattering amplitudes. Okay, by this, what I mean, since I didn't define to you what is an amplitude, but I already told you that we are going to be interested in correlation functions of gauge invariant operators in D equal 2. And so therefore, this sentence means that chi controls the structure of these correlation functions, okay? And to see it, what do I mean explicitly, I have to anticipate a little bit on these gauge invariant operators. Okay, you may think of them quite in an abstract way as something to insert in the path integral, which is invariant under the gauge transformation of my theory. Okay, but now I'm going to give you a little bit more. I'm going to define them a little bit more, and I will divide them into sets, these gauge invariant operators. Okay, I will talk about closed strings, gauge invariant operator, and open strings, gauge invariant operators. And I'm going to be a little bit more specific than this, okay? And as the lectures will go on, these things will be defined, but at the moment, just try to think of them in just using the information that I'm giving you. So now I'm giving you another information, and that is closed strings gauge invariant operators are associated from the two-dimensional point of view, from the geometrical point of view, to what they are to bulk punctures, and open string vertex operator or open string gauge invariant operators will be associated to boundary punctures. What are punctures? Punctures are just marked points on my two-dimensional surface. So again, a small drawing can be of help. So I imagine that this is my worksheet. Okay, so that's my boundary, and let me choose some nice color. So the bulk punctures will correspond to marked point in the interior of my worksheet, and the boundary punctures will correspond to marked points on the boundary of my worksheet. Okay. So in particular, since so these are precisely the point in space, in this two-dimensional space where these gauge invariant operators will be inserted. Okay. So in this sense, we are talking about local gauge invariant operators. But we'll see that going on with the lectures, we will see that we will also need the non-local gauge invariant operators, but they will be simply related to the local ones. But this we will see later. Okay. Now, another piece of information that I'm giving you without any demonstration, of course, is that for oriented two-dimensional surfaces, this Euler characteristic, which was given by this let's say Einstein-Hilbert action, if you want, with a Gibbons-Hawking correction to the boundary. In fact, boils down, as I told you, there are no propagating degrees of freedom, so this must be a topological invariant, and indeed it is. The result is that this chi is equal to 2 times 1 minus g. Now I'm going to define you what is g. So g is the genus of the two-dimensional surface, minus the number of boundaries, minus the number of bulk punctures, where C stands, the C here stands for closed, and minus 1/2 the number of open string punctures. Okay, so again, what is G? G is the genus. Okay, I don't have to explain you what is B. B is a boundary. So a two-dimensional surface can have as many boundaries as he wants to, but it can be a surface of higher genus, and genus is say the number of handles of my surface. And since I'm very bad in drawing, perhaps I will still try to give you some idea, but I know that you see this picture many times in many books, so that's my picture. So this is supposed to be a boundary of my Riemann surface, or my two-dimensional surface, and then then here you can imagine to have like a donut-like piece, which is the one handle. Okay, so this is the one handle. Okay, so you can have a discrete number of these handles, and this defines the genus. Okay, and so as I was telling you, on this surface you can have bulk punctures that are here, and you can have boundary punctures that here I have just one boundary, so I will put them here. Okay, but I can imagine to have two boundaries, for example, and okay. So that's why this is a nice expression for the Euler characteristic of a surface. Okay. So now why I told you that this thing is important for string perturbation theory. The reason, yes. Hello.
Hello. Hi. Sorry.
Yes.
What's NC and N sigma? Just to be sure.
Oh, these are the number of so NC are the bulk punctures associated to closed string gauge invariant operators. Are this thing that here are green, and NO are open string punctures, so they are punctures on the boundary.
Okay, thank you very much.
Okay.
That's perfect.
Okay, so now the idea is that chi, I don't want to write in red, I prefer to write in black. So chi is a topological. So if we see it as really as a part, as an integral, so if you see chi in this form, we can say that we are able, in fact, to add this part here. Okay, so we can add this part here to our initial Polyakov action, and this thing will not change the equation of motion that we have derived. Okay, just because there are no propagating degrees of freedom in this chi. So, in fact, this is what I am supposed to do. I take my Polyakov action, which is just function of h and x, and I upgrade it a little bit, just adding some lambda times chi. So this thing here doesn't change the equation of motion. So this is the same eons. Okay. But now this thing gives me an organization of the path integral, okay? Because when I do the integral over the matrix, it's true that this term here doesn't fill local variation of the metric, because it's a topological invariant, but for sure this term here is sensitive to the topology of the worldsheet because of this expression here. Okay, so that means that since naturally the integral over the matrix will split into a sum over topologies, the H star, let's say, where H star is a fixed topology, just by this simple observation, if I am now using this action to define my path integral, which I can take it as a prescription, okay, so this action here is more general than this action, so this is the one that I'm supposed to use, and so my generic correlation function of gauge invariant operators that I'm not going to define more than these for the moment is, of course, coming to be, if I'm considering only for the moment, I'm considering only V to be closed strings, just to write shorter formulas. And so this thing will just become sum over the genus that can go from 0, so 0 handles to infinite handles, to e to the minus lambda to 1 minus g minus nc. Okay, I set number of boundaries to 0 and therefore no open string insertions. Okay, of course I could also introduce them, but at the moment I'm not interested in doing this, just because I want to show you something a little bit simpler. And then I remain with some path integral of the same gauge invariant operators, but this time at fixed topology, so at fixed genus. Okay, and what is this guy that I have to compute? V1 Vn at fixed genus will be what? Will be the integral over the metric at fixed genus, the x over volume gauge, V1 Vn, e to the minus s hx. So this is the structure that we have encountered before, but we see now that is in this little bit more general treatment. The structure here is dressed by this combination here, which is just a number. Okay, this is just a number, but you see that this number is controlled by the number closed string insertion. I'm sorry, here there is NC, of course, and also by the genus here. Okay, so you see now these things really looks like perturbation theory. So this looks like perturbation theory, where the coupling constant, so the parameter which I'm using to expand my path integral, is given, is called G string, of course, and is given by e to the lambda. Okay, so essentially we have seen that adding this topological term to the Polyakov action gives us a way to weight indifferently different topological sectors of the path integral. Okay, so in the following lectures we will see that this lambda here that I have introduced. So you see here I have introduced a parameter lambda, which looks like an external parameter, but in fact it turns out that this lambda is not an external parameter. We will see that in fact this lambda is the VEV, is the vacuum expectation value of a field. This is a massless excitation of closed strings, of a closed string, which has a famous name, which is dilaton. We will see this guy emerging from the spectrum, from the physical excitation of the string. For the moment, just take it as an information, okay? Or if you don't want to take it, just think about that you can add to the Polyakov action this term weighted by this lambda, and this lambda naturally organizes a way of computing this path integral perturbatively in this form here. Okay. So are there questions up to here? So if there are no questions, maybe there is a question. Okay.
Can I ask for two clarifications about?
Yes, sure.
Yeah. First of all, I think I missed the definition of the moduli TI. So if you could explain it again.
Yeah. So okay. In fact, I didn't give you a real definition of the moduli TI. I just told you by words that this equation here, this equation here as a finite dimensional space of solutions. Okay.
Okay.
So the moduli TI are just the coordinate of this vector space, if you want. Here,
okay.
Infinitesimal. Okay.
And the second clarification, still about this part.
Yes.
Well, we have divided our variation of the worldsheet metric in two parts. So the gauge transformation is the diffeomorphism plus the Bayer transformations. And these two transformations are associated to two different parameters, the Xi parameter and the omega parameter.
Yes, and this one here.
And when I write the product between the variation in gauge variation and the modular variation, I separate the two contributions. One depended on omega capital and one depended on P1.
Yes.
But maybe it's a naive question, but I didn't expect this to happen because I expected the two different contributions, one dependent on Xi and one dependent on omega small, to be separated, to be detached, while omega capital contains the parameter Xi. So I thought that the two variations.
Yeah. So you see, this is essentially the reason why it is convenient to define this operator here.
Mm-hmm.
Right. So this operator here is natural to be defined because it is It is
Yes.
traceless, so it gives rise to a irreducible representation. So that's a map from vector fields to traceless rank to tensors. So this is a map between two irreducible representations. And you see, but you have to pay a price because you have, so you have to take out this piece here, but then this piece here you have to put it again in the where is it now? To put it here.
Sure.
And so somehow this effect here couples the two things.
Yes.
That's just a fact.
Yeah, so I was wondering why we are allowed to just a little bit lower to detach, so to say that independently the product between P1 and the modular variation is 0 and omega.
Oh, here you mean here?
Yeah, exactly.
Oh, because that's what I'm telling you, that this guy here. Oh, sorry. Now it's okay. So because these two guys here belongs to two different irreps. Okay.
Okay.
So it's essentially this is a scalar, but this is so they belong to two different irreps, and therefore so here there is a trace part, and here there is a traceless part. So they have to vanish independently.
Okay, now I see. Thanks.
Okay.
Thank you.
Okay. Other questions?
Yes, I've got one. Could you please, hi.
Hi.
Would it be possible for you to repeat this fiber bundle business for the modular space and the orbit?
Okay. So so here, there's this picture. So you have to imagine that this is my space. This is my space of metrics. Okay. Now, when I choose a fiducial metric, which is this h hat of t, okay, this h hat of t essentially, hello?
Yes.
Okay, this h hat of t spans, so these are span, so t is given by the solution to this equation. Okay, so you know that this is an n-dimensional space that depends on the topology. Okay, so the number of independent ti is in fact given essentially by this Riemann-Roch theorem that we have seen. But okay, once you have seen this, and thanks to this orthogonality condition, you see that your space of metric is essentially, I mean, I've used the word fiber bundle, but you see, it's just the basic fact that that these two variations are orthogonal. So you can move along the gauge fixing condition if you want. So this is the h hat of t. Okay, so this is the space. So this is the finite dimensional space of inequivalent metrics if you want. And for every metric at fixed moduli, you can move. You have an infinite dimensional fiber. Okay.
Yeah. Great. Thanks.
Okay. Okay. So right. So now we have to come to the hard part. So now we really have to put our hands on this guy. This guy here. We would like to attack the computation of this path integral, and let's see what we can do about it. And so this is essentially what Polyakov did. So let's try to understand how we can compute this integral. So at fixed topology, the h, so from now on, g is fixed. And so let's try to at least heuristically evaluate this path integral gauge. And for the time being, I am allow me to skip the operator insertion. So I'm just talking about, if you want, about the partition function without operator insertion. So we will discuss what you have to do with these gauge invariant operators later when we will discuss real computation of amplitudes. At the moment, I just want to, since I want to arrive a little bit quick to the BRST quantization of the string, let me just ignore for the moment the possible operator insertions. So I'm imagining that I'm just inserting the identity operator, which is of course gauge invariant. Ignore the V's for the moment. And okay, so if we believe in the receipt that I have given you, then I am supposed to compute something like this. The H, okay, let me call it the H along the modular space, the H along the gauge orbit, the X, which is my only really propagating field, all the rest is pure gauges. And this I have to divide by the V gauge, and I have to put e to the minus s, H of X. Okay, so now what I do, and essentially now I just have to do seriously this change of variables that we discussed here. Okay, so here we have already seen what these change of variables are. So now I have to plug these two equations inside the path integral, essentially. And so essentially I am now saying that my H alpha beta is obtained from a fiducial value, ht, h hat alpha beta of t, and then to these I apply. Okay, so essentially I where is the drawing? Okay, here. So first, so to choose an H, what I'm doing to choose an H is a generic point here. Okay, so first of all I go along the gauge fixing slice and up to some position, and then I go up. Okay, so this is how I reach the most generic metric, and which is my variable of integration. So that means a fiducial value with some gauge transformation that I pictorially indicate with this psi w, which are the parameter of my gauge transformation. Okay, which I can also, for convenience of notation, write in this way: h time prime alpha beta t. So prime for me will mean gauge transformation. Okay. So here we go. Now we can plug our expressions. So I have first to write this part of the measure, which goes along the modular space. So I told you that modular space is finite dimensional. So let me call M this n-dimensional manifold, Ti, and then of course I have to add the determinant of the Jacobian, and then now I have to write this part of the variation of the functional integration, which I will again use the fact that this is this variation is in one-to-one correspondence with the gauge orbit. That's by definition the gauge orbit. So that means that it is a copy of my gauge group. Okay, and so I have just to take care, of course, of the change of variable. That's the only thing that I have to do. V gauge and the gauge H over let's say the Xi, the W. Okay, so these are my determinants, and then I still have this guy here, the X, and finally I have my action e to the minus s. Just to be careful, because here I'm using the fact that my metric here is explicitly given in this form here. Okay, so I have to write it in this way. So this is h hat prime of t, comma x. Okay. And so now I'm just looking at this integral and do minimal considerations on this integral, and to see that this integral now simplifies. Okay. To see this, first of all, look that here I have my metric. So here I can imagine that here I fixed a gauge h hat of t, and then I performed a gauge transformation. So I can imagine to do, but notice that here I have x here, and x here is also is integrated. So x is a variable of integration, so I can just relabel it and nothing changes. So I can put a prime on x and a prime on the measure, and essentially that's all, because now you see that now I use the fact that these things that I have, wait, sorry, I'm losing. Yes. So now this thing here is clearly gauge invariant, because that's my original gauge invariant action. Okay, and also it is possible to show that these determinants are also gauge invariant. So you see now the only thing that depends on the gauge parameters is in principle only the measure here. But in fact, it turns out this is also something that I cannot really prove for you, but this is also gauge invariant. Okay, so these are all gauge invariant things. In fact, these three here are almost trivially gauge invariant. This is gauge invariant by construction, and if you think a little bit about, you will see that also these guys are gauge invariant. This is a little bit more tricky, okay, because this is surely at the classical level is gauge invariant, but since this is a functional integral, it doesn't mean so much to say classical. In fact, it turns out that just take it as an information, but in fact, this measure is gauge invariant only in D equal 26. Okay, but we will encounter again D equal 26 from another reason, so everything will be consistent at the end. But you see, if we now see that everything is gauge invariant, then you see that the dependence on the gauge parameters completely factor out and completely disappear, and now we can just simplify the volume of the gauge group obtained by doing this integral, okay, because here nothing depends on psi and w and the volume of gauge. Okay, and so our path integral now became a little bit simpler. It's a finite dimensional integral on the modular space. Then I have the x. Now this is the only variable that on which I have to do a path integral. Okay, but then I have to pay a price, of course, for this, because I still have these determinants. So I am not over, as you may imagine. And then the action. Where now you see what is the difference between the previous action that was completely gauge invariant, this action that we wrote at the very beginning. Okay, this Polyakov action, you know what I'm talking about, and this action here. The only difference that here it's this is the Polyakov action computed for a peculiar choice of the metric. Okay, so this is if you want the gauge fixed, this is the gauge fixed Polyakov action. Okay. So now what we have to do now? Now we have to exponentiate the determinants. I'm sure you all had a class on quantum field theory and quantization of gauge theories. So you know that this exponentiation of determinants is essentially done by using the Fadeev-Popov trick. Okay, so what is this Fadeev-Popov trick? The idea is very simple. Starts from the observation that if you are in finite dimension and you have some metric and you want to compute some matrix, and you want to compute the determinant of a matrix, if you have the determinant of some matrix whose indices for later convenience, I'm going to call them big I and small j, just to allow myself to be a little bit more generic in infinite dimensions, which is the case of string theory. But the statement is the following: that this determinant, in fact, can be computed from an almost ordinary integral, where I use some dBIs and dCj. So this is infinite dimension. That's a finite dimensional integral, and so I have as many big I indices I have, and as the values of the big I indices, and as many C as the values of the possible values of the J index. Then the interesting thing is that I have to put this exp to, I don't remember if there is a minus here, but let's put a minus just. Bi M I J Cj. So I leave to you as an exercise to prove this thing in infinite dimension. So you may take a 2 by 2 matrix and try to write this determinant as this integral. But sorry, there is something very important about this integral that I still didn't mention, but I'm sure you know it already. That these guys here are not ordinary integration variables, but these are Grassmann variables. So they are fermionic, let's say. Okay, so they are Grassmann variables. So this integral here is in fact a Berezin integral. Berezin integral, what does it mean? That if my Grassmann variable is theta, Berezin integral, as for sure you know, is the rule is that d theta is equal to 1, and d theta 1, let's say, is equal to 0. Of course, theta is Grassmann odd, so that means that theta squared is equal to 0. So you cannot find other possibility. Either you find the theta in your path integral, and then the Berezin integral is 1. Either you don't find it, and then the Berezin integral is 0. And now, if you have never done it before, this is very nice to do. It's very quick, and it's you can learn how the Fadeev-Popov method really works. So you can try this on a for a 2 by 2 matrix. Okay. So the idea of Fadeev-Popov is to take this finite dimensional expression seriously and extend it for infinite dimensional, and therefore interpret these determinants here, this one and this one. We will see it's a sort of hybrid in this way, by making some functional integration. Okay, so a little bit of nomenclature. These objects that I have defined here, these Grassmann variables, they have a standard name. So Bi is called the anti-ghost, and J is called the ghost. Okay. So now the idea is that using this identity and we can take these determinants. This is the product of two determinants. So this is like the determinant of a block diagonal matrix, which is sorry, I always forget to take out the eraser. This is can be written as a block diagonal matrix, and so the idea then is the following: that if I have to write down these determinants, the H of the Ti and the gauge H over the, let me call it gauge, just to be a little bit more. Essentially, what I have to do is that I have to take my my parameters here. So here I have Ti is a parameter, and then I have from the gauge I have two other parameters that we have already discussed. So perhaps it would have been better if I really wrote the real parameters that are Xi and W. Okay, so this is a sort of formal notation. But what is important is that you see I have Ti, Xi alpha, and W, and to each of these guy I associate a ghost. That is the guy that has to give me this variable of integration. Okay, so this ghost, of course, since these guys have different geometric meaning, so this ghost will inherit the geometric structure of these objects, and so we can call them in some way. So, for example, this guy we can call it psi I, this guy we can call it C alpha, and this guy we can call it lambda. Okay, notice that this guy here, see, this guy here is this is a function of my worldsheet coordinates. Okay, on the other hand, these moduli here, I told you they are just constant on the worldsheet. Okay, so they are not they don't depend on the worldsheet point. So this is important to build the correct quadratic form for the Faddeev-Popov action. And what I have to do, and then the Faddeev-Popov action tells me, okay, so now you with the ghost you have and then you have to contract everything with the anti-ghost, and the anti-ghost is provided by an anti-ghost, which is B alpha beta. Okay, so if now I apply and properly generalize these, then I can rewrite this action here. Let me put it a star and come and go to this other slide here. I can write this thing in the following way. So I still have my let me try. Unfortunately, I cannot really see it, so I have to copy it from somewhere here. Okay, so some m dt I, then I have the x, and then I have to do the path integral on all these variables, okay? Because the Faddeev-Popov procedures, I mean, this trick tells me that essentially I can exponentiate all of my determinants at the price of introducing new path integration variables, okay? So I have to put the functional integration, the integration or functional integration, depending on whether these are worldsheet fields or just numbers. So here in particular, I will have to put, you see, I will have to put the psi I, the C alpha, D lambda, and D B alpha beta. So these are all the this is the measure. This is the measure, and then let me write on the second floor here the first part of the integrand, which is essentially which are just these two determinants here, okay, which have been now exponentiated. So the first part coming from the moduli space is this guy here, T square sigma square root of H hat B alpha beta times T I H hat alpha beta of T. Okay? So this is in total a number which depends on this I index here, and it's contracted with the GOST associated to it, which is the GOST modulus, which is psi I. And then I have the other part of the determinant that comes from the gauge, from the real gauge variation, which is this one here. And this gives E to the sum canonical 1 over 2 pi times D square sigma square root of H hat B alpha beta. So I have to do the anti-GOST against this guy here, which is the variation, and this guy here is just the variation of the metric with respect to the gauge parameters. You see here. So that means the variation of the metric, I know it very well. It's just given by that expression that we discussed before, P1. So here P1, instead of psi, I have to put the GOST. So P1C alpha beta minus 1/2 lambda minus 1/2 the divergence of the C GOST H alpha beta. Okay, so now all the determinants has been exponentiated, and they are going to give corrections to my action. And finally, I still have my original gauge invariant action, which has been gauge fixed, which is E to the minus S H hat of T X. Okay. So now this is still not in the form where we usually have this, where we usually consider this path integral in string theory. And the reason is that now there are some very trivial integration that I can do. So one of these is the integration in the psi here. You see psi only depends here, so this is essentially a Lagrange multiplier. Okay, so this is a Grassmann, these are Grassmann odd, of course. And another one, which is pretty trivial, is the integral in d lambda, which also appears only here. Okay, so doing these simple integrals, so if I do the integral in d psi I, essentially what happens is that, so you see that I do the integral. If I expand this exponential, so I have only one term. We start with 1, which gives 0 on the Berezin integral, and then I have the only term that is linear in psi I, that is the one that is captured by this integral. So if I do this integral, essentially I bring down this this factor here. I bring at the floor this factor here. This square sigma square root of H hat B alpha beta di on H alpha beta. And you see this thing can be conveniently written using this inner product that we defined between rank 2 traceless tensors as B alpha beta comma the IH alpha beta. So this is going to be something that will be downstairs in my Polyakov path integral. And I can still do also the functional integral in lambda. This is very easy because the action depends only linearly in lambda. So if you see, essentially that means just to use the equation of motion because lambda only appears at linear level. So you see that if I take this, so the equation of motion essentially tells me that B alpha beta times H alpha beta is equal to 0. So H alpha beta B alpha beta is equal to 0. So that means that B alpha beta is traceless. Okay, so these were like the simple operation that I can do on the Polyakov path integral. And therefore, I am left finally, if now I restore, if just for the sake of glory, I restore the gauge invariant operators, which I completely ignored at the moment, I can write these fixed genus. I finally have a form that can be used for practical computation for this correlation function of NC gauge invariant operators, which is mg, the TI, so the integration in the modular space, and then the path integral on the worldsheet fields, which are the embedding coordinates, the anti-ghost, and the ghost, then a bunch of gauge invariant operators, which I'm still not discussing. Then I have insertions of these guys, and I have one for every I, so for I to 1 to the dimension of the modular space, let me call mg to the dimension of mg of B di h. And finally, I have E, and then I have the action, which is the gauge fixed action, which is h hat x, and then minus the action of the BC system. That is exactly this action here. That comes out from the Fadeev-Popov prescription. Okay, and so just to remember, since we have used the fact that B alpha beta is traceless, okay, we can be a little bit more specific. And so just if we want to be concrete, SBC, so this is as, let's say, Fadeev-Popov, okay, Fadeev-Popov. This is precisely 1 over 2 pi, the integral in the 2 sigma square root of h hat B alpha beta P1 P1C alpha beta. Okay. Okay. So I guess this could be a good time for questions if you want. And so if you don't have question, we can continue. Okay, so essentially this is the form of the, so this is the form of the Polyakov path integral, which is valid for any choice, of h hat, any reasonable choice. This is valid for any choice of h hat alpha beta. Now, as usual in any gauge theory, there are gauge fixings that are more convenient than others, and the same is true here, of course. So what is the gauge fixing that we like very much in string theory? The one that we like very much is the so-called conformal gauge. So what is the conformal gauge? It's very simple. Essentially boils down to choose for my metric, for my fiducial metric, delta alpha beta, where alpha is equal to 0 and 1. Okay, so just one word of warning. In writing this, I have passed to Euclidean, as you might have noticed, Euclidean signature. Okay, on the worksheet. Okay, so that means that instead of tau and sigma that I had before, now I have, I think it's minus IT or IT. Now, honestly, I don't remember, but it's not so important. And but the fact is that the fixed convention is that my H is equal to dt square plus d sigma square. Okay, so before this was minus d tau square plus d sigma square. Okay, from here you can easily trace back what is the weak rotation that I did. Now the thing is that this thing here, I'm going to write it by another obvious change of coordinate as minus 2 dw bar, where w is a complex coordinate, which is t plus I sigma, and w bar is t minus I sigma. So these are all elementary operations. Now, as you may have noticed that there are a lot of covariant derivatives emerging a lot everywhere, and it's clearly now when I choose this flat matrix, all covariant derivatives magically disappears, and doesn't take so much to convince ourselves that all of our worksheet fields will also simplify quite a lot. In particular, if we take, okay, let me save some space by putting this thing here, and perhaps also making it a little bit smaller. Okay. I don't know how to get rid of this. Okay, and okay, so the first thing is what happens to the big ghost. It was a symmetric two index. So now in these w coordinates, essentially I will have a b w, a b w bar, and a b w bar. In fact, this BWW bar is not so difficult to realize that this is just the trace written with this metric. And therefore, we knew that anti-ghost is traceless just because we have integrated out the ghost for the Weil transformations. So this is equal to 0. And now this guy here, we can give, since we don't like to always write W bar, it's easy to just use a shorthand notation to call this guy B and to call this guy B bar. And the same we can do for C alpha. C alpha, alpha can have two values, can be CW or CW bar, and I will call this guy C, and I will call this guy C bar. And the same I can do for the covariant derivatives. dw just becomes dw, which I will call it just del, and the covariant derivative on w bar will just be w bar, which becomes del bar. Okay, with this simplification, the gauge fixed action become what I will call from now on as matter, equal to 1 over 2 pi alpha prime d2w del x mu del bar x mu, notice that the dependence on the metric has completely disappeared. Okay, so this before was having a dependence on the metric. Now this dependence is not there anymore. So this is a function. This is a functional only of x and nothing else. But this guy has to be paired with its ghost friend, 1 over 2 pi d2w b del bar c plus b del c bar. This is what this action boils down. You see this thing here. When we say h hat equal to 1, this guy essentially becomes a del or a del bar, and therefore we get this action here. Okay. Are there questions? Okay.
Sorry, Carlo.
Yes. Please.
The x's, you keep them in the mu coordinates, but the derivatives. Okay, I'm just wondering, you're not changing you're keeping the mu coordinates for x's.
Sure. The x is exactly the x that we had before.
Yeah.
So the x, so perhaps sometimes I forgot to put the Lorentz index on x just because it is completely an external index from the worksheet point of view. Okay, so here, of course, this is x mu. So these x mu's are a bunch of scalar fields that I have in 2 dimensions. Okay, these are d equal to the number of space-time dimension scalar fields. Okay.
Okay.
And in fact, now you see that now if you forget about everything, if you forget about this 2-dimensional gravity and so on and so forth, if you just look at this action here, this looks like the action of these scalar fields in 2 dimensions. Okay, of these scalar fields in 2 dimensions.
Okay.
And this looks like a first-order system. It's more or less similar to some fermionic system, where instead of having a kinetic operator, which is del bar, you just have a simple kinetic operator. So this looks like, roughly speaking, the Dirac Lagrangian in 2 dimensions. Okay, where B and C are sort of fermions. Okay.
And the gauge group generally now is abelian, not non-abelian. Or
what gauge group are you talking about?
I'm just thinking in general when you've done gauge fixing.
So this is the gauge fixed action. Okay, so this is the gauge fixed action. So this is a gauge fixed action. So it is not supposed to have gauge symmetry anymore because it is gauge fixed. Okay, and this is the Fadeev-Popov. Now what will happen, in fact, is that so it seemed that we have fixed the gauge completely, but in fact it is not true. So there is still gauge redundancy in these actions. Okay, and this is going to be extremely important. So now we're not talking about this, but I can perhaps just anticipate a little bit that there is a gauge redundancy that we didn't have fixed, and we will discuss this more. This gauge redundancy is captured by the fact that even if this looks like a very simple action in 2 dimensions, this action has an infinite dimensional symmetry that is a sort of invisible at the moment, because this action and also this action are conformal invariant. Okay. So this conformal invariance is a mixture, is a residual symmetry from the diffeomorphism and phi, and therefore we will have to treat it consistently as any other gauge symmetry. So this will be, so we will see how to do it. Okay. But at the moment, just follow the Fadeev-Popov procedure. So are you satisfied by my answer?
Yeah. I was just curious. Thank you.
Very good. Okay. Okay. So, okay, you may think, okay, so now nice, you have done all these formal manipulation to end up with these two decoupled actions. And what should we do with them? But what you should do is to use them to compute this path integral, of course, okay? Because that's why we did this. But in order to do this, we have still to exploit some structure that is not completely visible yet. And so let me, okay, so since I have them here, I can perhaps avoid to. So now the fact is that gauge symmetry as I was telling, has been, let me put in quotation mark, fixed modulo this comment on conformal invariance that I have given you, which is crucial though, but let's suppose that the gauge symmetry has been fixed, in fact. So you may ask what we do with this. So this gauge fixed action now doesn't have any gauge symmetry, okay? In fact, this is not completely true because essentially in this coupled system, gauge fixed action plus Faddeev of Lagrangian, there is a new global symmetry, okay? So this is something very generic in any quantization of gauge theory. This has nothing to do with string theory in particular, but it's true for every time I quantize a gauge theory using this method, I end up with a gauge fixed action with a ghost action, and this coupled system matter ghost doesn't have the gauge symmetry anymore, of course, but it has a new global symmetry. This new global symmetry, as many of you know, is called BRST symmetry. Okay, and okay, so this BRST symmetry looks pretty easy. It is a fermionic BRST symmetry. Is fermionic in much the same way as the supersymmetry transformation that you saw this morning are. So it's in some sense similar to a supersymmetry transformation. The only difference is that it's not done. It's done with a fermion, but not with a spinor. It's done with a fermion whose spin has been changed to be integer instead of half integer. But modulo this detail, it works in a sort of similar way, and we can write down what are these transformations. And then I think that we are approaching the end of the lecture. So I will finish writing you this transformation. C del x mu plus C bar del bar x mu del B of C is equal to C del C, del B of C bar is equal to C bar del bar C bar, and finally the BRST variation of the anti-ghost is equal to this very nice combination that will play a very important role in all the things that we will say from now on, 2B del C plus del B C. This is the BRST variation of the ghost, and of course its friend, the anti-ghost, will have the anti-holomorphic variation del x. So here I have a scalar product, I hope you understand, plus 2B del bar C plus del B C bar. Okay, and so I end up with the following exercise for you, which is a simple exercise to check the variation of this free theory. So you see that's a free theory. So look that. So this is a free theory of two decoupled system. Okay, so these two systems, they really don't talk to each other. You see, this is a free theory for X. That's a free theory for B and C. So these two guys never talk to each other. But the nice thing is that just what happens with supersymmetry in the Welsumino model. Here also you see that this BRST symmetry somehow couples this guy, which would be otherwise completely decoupled. Okay, you see the BRST variation of X mixes the ghost and the X, and the C is internal, but the BRST variation of the anti-ghost contains an X part and a ghost part, etc., etc. So through the BRST transformation, these two systems start to talk to each other. Okay, and the way they talk to each other is crucial, as we will see. Okay, so there are a few properties. Okay, the first property is that the BRST variation of S tot is equal to 0. By S tot, I mean S matter plus S cost.
Sorry, in the last line there, do you have a bar also on the C?
Yeah, sure. Thanks a lot. Of course. Yes. And okay, so that's the first thing. But there is another property which is even more important than the BRST variation, the fact that the action is BRST invariant, the fact that these variations are nilpotent. Okay, so if I apply twice the BRST transformation, I find identically 0. Okay, this is a crucial property. And I leave to you this as a simple exercise because it is extremely simple. Okay, so this one you just substitute, you act del B on the action, and then you act phi, and you will see that it is invariant. Now there is a word of warning for you. If you really try to check that this guy here is BRST invariant, this won't be BRST invariant of shell, let's say, but you will have to use the EOM. Okay? You will have to use the EOMs, and so perhaps I can finish the lecture by telling you what are these EOMs. Okay, these are very simple because you see this is a free theory, so the EOMs are just equation for free fields. Okay, so the EOM for X is del bar X mu equal to 0. Then there is an EOM for C and C bar, and this is respectively del of C bar equal to del bar of C equal to 0, and del bar of B equal to del of B bar equal to 0. Okay, you have to use them. Okay. So then what does it mean? But you see that the first equation, it means that X mu was a function of, so all these fields are in principle function of W and W bar, right? These are function of two variables. But the EOM of X is telling you that X can be written, that's the wave equation, right? So this is the wave equation in 2 dimensions. So that just means that X mu can be written as some X left mu of W plus X right mu of W bar. And C bar and C of W. So, and the other one will tell you that C is in fact just a function of W, C bar is just a function of W bar, and the same is true for B. B is just a function of W, and B bar is just a function of W bar, okay? So these guys are, let's say, holomorphic fields. And this one as well, in the sense that it's split in the sum of one holomorphic and one telomorphic. Of course, these guys are holomorphic, these guys are anti-holomorphic. Okay, so I think this is a good time to stop. And so now I am going to switch off the registration. Hopefully I will be able to do it. Interrompi la registrazione. Ok.